Let us understand how to find the kinetic energy of the electron ejected when yellow light of a frequency 5.2 into 10 to the power 14 second inverse falls on the surface of a potassium metal. The threshold frequency of potassium is given 5 into 10 to the power 14 second inverse. So the total energy of the incident photon is always taken up to be HF 6.626 into 10 to the power minus 34 into 5.2 into 10 to the power 14 hertz. So this would give me the total energy of the incident photon. The threshold energy of the potassium surface would be given by the formula HF naught. So H here is the Planck's constant. Frequency has been given to us. This is the threshold frequency, which means the minimum frequency at which a potassium surface would emit an electron. So the kinetic energy of the emitted electron would be given by the formula HF minus HF naught. H remains common and we get 5.2 into 10 to the power 14 minus 5 into 10 raised to the power 14. That turns out to be 1.325 into 10 to the power minus 20 joules. Next, today we have another numerical. It says when electromagnetic radiation of wavelength 300 nanometer falls on the surface of sodium, electrons are emitted with a kinetic energy of 1.68 into 10 to the power 5 joule per mole. So this is the kinetic energy of 1 mole of electrons. And you know from your previous classes that 1 mole is equal to Avogadro's number of electrons. So he's asking us the minimum energy required to remove an electron from the surface of sodium. So we already know E is equal to HF. F is C by lambda. So E is equal to HC by lambda. Substitute H as Planck's constant, C as velocity of light, that is 3 into 10 to the power 8 meter per second, and wavelength as 300 nanometers. Now 1 nanometer is 10 to the power minus 9 meters. So substituting we get 6.626 into 10 to the power minus 19 joules. Energy of 1 mole of photons is given by H, that is 6.626 into 10 to the power minus 19 obtained using the formula Hc by lambda multiplied by Avogadro's number. So 1 mole of photons means energy of 1 photon multiplied by that of Avogadro's number. This turns out to be 3.99 into 10 to the power 5 joules per mole. But I have been asked to find the minimum energy required to remove electron from sodium. So we already know that E is equal to E naught plus kinetic energy. That is HF is equal to HF naught plus kinetic energy. But I need what? The minimum energy. This means I need the threshold energy required. So for that we have to follow the second thing, that is E is equal to HF, which means 3.99 into 10 to the power 5 joules per mole. Kinetic energy is 1.6 into 68 into 10 to the power 5 joules per mole, which we have already been given in the numerical. E naught is the energy required to remove 1 mole of electrons. So E naught is E minus kinetic energy, where E we have calculated previously. So using the values we get 2.31 into 10 to the power 5 joule per mole. So for 1 mole the threshold energy required is 2.31 into 10 to the power 5. So minimum energy required to remove 1 electron should be 2.31 into 10 to the power 5 divided by Avogadro's number, which is 3.84 into 10 to the power minus 19 joules. If we are asked to find the wavelength of the electron emitted, then we would use our standard formula lambda is equal to Hc by E. I wish to emphasize on this topic the difference between energy and wavelength here is this is the energy required to remove an electron from the surface of sodium. But once the electron has been emitted and it starts moving towards the positive anode, the positive potential, then the wavelength associated by the wave of the electron can be given by the formula lambda is equal to hc by E, and it turns out to be 517 into 10 to the power minus 9 meter. We all know that 10 raised to the power minus 9 meter is 1 nanometer. So the final answer becomes 517 nanometer. Thanks for now.